Chen. Now I'd like to talk about the introduction of experimentary. In the chemical process, the reactor is a key of equivalent where raw materials undergo chemical reaction for the desired product. And now the I'll say about the packed reactor. The packed reactor is a material column which filled with the glass rings as a packing. And it is the most important packed reactor that in order to success the industrial operation. And for the residence time distribution about the experiment. Residence time distribution is the time for a reagent react to change into product. The key to develop the dynamic model for design and operation, and it also to determine the operation cost, volume of reactor, flow rate, and type of packing. I'd like to continue for the objective of this experiment 3, which is the RDT in packed reactor, which is to determine the effect of liquid and gas feed rates on the mean residence time and degree intensity of the liquid phase and dispersion.
I will be explaining about the theory in this experiment. Residence time distribution of a reactor is the characteristic of the mixing that occurs in the chemical reactor. Residence time distribution can be determined experimentally by injecting an inert chemical molecule or atom called a tracer into the reactor at time t equals to 0, and then the concentration C in the effluent stream is measured as a function of time. The tracer should have physical properties similar to those of the reacting mixture and be completely soluble in the mixture. It also should not be absorbed on the walls or other surfaces in the reactor. The two methods of injection that are carried out in our experiment are step input and pulse input. Okay, so this is the graph for step input. This is before and this is after. For step input, a constant rate of tracer is assumed and added to the feed that is initiated at time t equals to 0 with constant volumetric flow rate. The tracer in the feed is injected continuously at a constant level until the concentration in the effluent is indistinguishable from the feed, and then the experiment may discontinue. For pulse input, this is before and this is after the experiment. For pulse input, an amount of tracer N0 is suddenly injected into the feed stream, entering the reactor in a short amount of time, which is for at least a few minutes. The outlet concentration is then measured as a function of time.
Hi, my name is Singh. Now I'd like to talk about the methodology of this experiment. Before we start this experiment, there are some of the general start procedure needs to be followed, which is 10 liter of 0.2 molarity of sodium chloride is prepared in the dosing tank T2, and the compressed air in here is ensured to be on all the time with the pressure of 2 bar. For both of these experiments, A and B, which consists of counter current mode and cold current mode. Now, I'd like to talk about the counter current mode first for both experiments A and B. Step 1, the general procedure is performed. Next, the valve of the counter current is prepared with V10, V3 and V5 remain closed. Next, valve V1 is open. Simultaneously, pump V1 is open, and then the solution, and then the deionized solution is filled in the pack bed and until the packing height. Okay. Now, next is that the valve V1 is be controlled to 500 milliliter per minute. And next, the valve V6 and V8 is open and is to be controlled to 1 liter per minute for the flow rate. And next, the conductivity reading CT1 is observed and is led to be stabilized at low value. Next, the dosing pump P2 is switched on and valve V14 is open to ensure that there is no air inside the system. And then the valve V14 is closed. Simultaneously, the valve V9 is open and let the sodium chloride solution to flow inside. And then the conductivity reading CT1 is recorded at 1 minute, and the start button in the soda system, which is recorded on the computer that is provided. Then the recording is continued until the conductivity is constant. After it is constant, all the experiment is being stopped and the liquid is being drained out. Now I want to say about for experiment B of counter current mode. For it, step 1 to step 8 is repeated from experiment A, and then the pump P2 is being opened for about 2 minutes. And valve V9 is closed after 2 minutes. Then the recording is being recorded until it's reached constant. And when the conductivity is constant, then all the experiment is stopped and all the liquid is being drained out. About the counter current of the experiment. Now I would like to explain about the co-current mode for experiment A and B. In experiment A, the general startup procedure is being performed, and then the valve is appropriate to adjusted to co-current mode, which V2, V4 and V9 is closed, and then V3 and V5 are open. Next, pump P1 is being switched on simultaneously. Valve V1 is open and it is controlled to about 500 milliliter per minute for the flow rate. And then the valve V6 and V8 is open, and V8 is controlled about the air about 1 liter per minute. And then the conductivity reading CT2 is being recorded on the computer that is provided. And next, the dosing pump P2 is being switched on, and valve 15 is open to let the trapped air inside to being blend off. Next, valve V15 is closed and valve V10 is open, and then the timer is started simultaneously. The conductivity reading of CD2 is being recorded at 1 minute interval, and the start button of SODA's data acquisition system is clicked, and the recording is continued until the conductivity reading is constant. After the conductivity reading is constant, the experiment is stopped and all the liquid is being drained out. And for experiment B of co-current mode, step 1 and to step 7 is repeated from experiment A. Just that step 8 is the dosing pump P2 is being opened for about 2 minutes, and then the valve V10 is closed, and the recording is continued until the conductivity reading is constant. After the conductivity reading is constant, the experiment is stopped and all the liquid is being drained out.
And today I'm going to explain the result and discussion for this experiment 3. For this experiment 3, we have two parts, part A and part B. For today, I'm going to explain for the part A result. So for part A, we have two modes, which is the counter current mode and the co-current mode. So before we proceed, let me explain about the calibration curve. So before we proceed with the graph, we have to find the calibration curve equation. So after we plot the equation, after we plot the graph, we will find the calibration curve equation, which is y equals to 1633.8x plus 484.06. Next, after we find the calibration curve, then we can proceed to the graph. So for this experiment, we have three graphs, which is conductivity versus time graph, concentration versus time graph, and resident time versus time graph. So for conductivity versus time graph, we obtain from the data of the experiment previously. Next, for the concentration versus time graph, we obtain from the calibration curve that we obtained previously as well. Then we substitute the value of conductivity to find the concentration data. Next is the resident time versus time graph. The resident time versus time graph we obtain from the Simpson's rule. Now, I will explain about the conductivity versus time graph, concentration versus time graph, and as well as resident time versus time graph. So, as we can see, all three graphs has the same pattern, which is from first minute to the second minute, it remains constant. Discuss about the co-current for all three graphs. So for all three graphs for co-current mode, we have the same pattern for this graph, which is from the first to the third minute, it remains constant. Then after we inject the sodium chloride, it increased fluctuatingly until the 25th minutes. After that, it starts to remain constant. This is because it has reached the steady state value.
Now I'll be explaining on the part B of experiment 3, which is the pulse change input. Using our pulse change input, we have also obtained three graphs, which is the conductivity versus time, the concentration versus time, and residence time versus time. Earlier, Hafiz has explained on how we have used our calibration curve for conductivity and concentration to obtain these three graphs. For these three graphs, we've also done in two modes, which is countercurrent and co-current. Now I'll be explaining on the countercurrent mode. Okay, for our countercurrent mode, as you can see, all three graphs basically have the same trend line, where it starts from the first minute, and you can see a sudden increase in the graph from the 5th minute. This is due to the when we switch on pump 2, it injects a sodium chloride solution into the system. This causes the conductivity to increase rapidly and reaches its peak on the 7th minute, where pump 2 is then switched off. Once pump 2 is switched off, the supply of sodium chloride is cut off the system, which causes the conductivity to increase until it reaches a steady state value at the 15th minute, where we have stopped the experiment. As we can see, the trend line is similar because conductivity influences concentration, which then also influences residence time through the Simpson's rule. This is why we can see that we have obtained the similar trend line for all these three graphs. For the co-current flow, we also have obtained three graphs, which is conductivity versus time, concentration versus time, as well as residence time versus time. From our graph of conductivity versus time, we can see from the first minute until the 7th minute it increases, and then it suddenly increases until its peak at the 14th minute. This increase is not very linear, it actually involves a lot of fluctuation. But once it reaches its peak at the 14th minute, it increases until it reaches a steady state, and then we stop our experiment. Now we're going to move on to concentration versus time. As you can see, the concentration versus time graph, our concentration starts off at 0 and then it goes to a negative value. It also then increases with a fluctuation, and it reaches its peak at the 14th minute as well. After the 14th minute, it begins to decrease, and also once it has reached its steady state value, we stop the experiment. As we can see, the residence time graph is similar to the concentration time graph, because we have used Simpson's rule using the concentration, which causes the concentration to influence the residence time. This is why both of these graphs have the same trend line.
Continue with the few errors found in this experiment and the ways to modify this error. The first error would be inconsistency of water and air flowing during the experiment. The way to modify this error is the flow meter reading is constantly observed to maintain the consistency of the desired value. The second error would be trapped air bubbles inside the reactor. Bubbles inside the reactor should be removed and washed before conducting the experiment. The third and the final error would be leftover sodium chlorides in the tubular reactor. We should flush the tubular tube with deionized water until no trace of salt is found. For this experiment, is the time required to reach the highest conductivity is faster in countercurrent flow compared to co-current flow. The mixing in countercurrent flow is more effective and fast than in co-current flow. Plus input is a much more effective method compared to the step input method. This is because the amount of tracer to be injected into the system for pulse input is only a certain amount of time, whereas for step input, the tracer is being injected throughout the experiment.